Hello again everyone, welcome back to ptet.chemistry channel. So this is the last lecture tutorial as part of the stoichiometry and the mole concept topic tutorials. So in this lecture tutorial, I will not go through any new contents as we are going through all the lesson objective, all the learning objective as stated in the Cambridge curriculum. If you miss anything, you can browse through the topical playlist for those stoichiometry and the mole concept. In this lecture tutorial, so what I'll do is more of sample questions where there is miscellaneous concepts mixed in here and there. So it's pretty much like actual work, but just to summarize all the concepts that we have learned. So I've just gathered together a couple of questions to show you how the different concepts jumble up together in these various questions. For example, in this first one, so sodium oxide is a metal oxide. Eventually, you will learn that metal oxides are basically what you call basic oxide because they dissolve in water to give you alkali. Alkali basically is a solution of hydroxide. So a solution of hydroxide is alkaline, and you also call it as alkali because there's the noun, and alkali is basically an alkaline or a basic solution where the pH is greater than 7. So you gotta write an equation. Even though they don't say balance, you gotta be able to balance it. This is sodium oxide, so Na plus O2 minus. A long time ago when we did ionic bonding, you have done the dot and crosses for this. You will remember that you need 2 of the Na plus in order to satisfy the 2 electrons gained by the oxygen atom. You will also remember that we did balancing formula in terms of the charges of the ions must cancel out in the manner that we need 2 Na plus and 1 O2 minus such that we get Na2O for the formula of sodium oxide. They react with water. Water is part of covalent bonding. It is among the 11 or the 12 simple covalent molecules, structure of which are expected to draw as well as the dot and cross. When that reacts, that gives you sodium hydroxide, Na plus OH minus. Because there's plus 1 and minus 1, they are present in a 1-to-1 ratio. As a result of the formula of Na2O, you have 2 sodium, but you only have 1 sodium here. So you put a 2 in front, where you cannot change the number at the bottom because these charges are already balanced out. That give you the formula. I can change the number in front to balance the equation. 2 sodium, 2 oxygen, 1 oxygen plus 1 oxygen, 2 oxygen, 2 hydrogen, 2 times 1, 2 hydrogen, you get the 1 mark just like that. The next bit is on calculations, and you cannot kind of do a calculation without a balance equation. So it's important that you could do the previous bit. This is the sodium oxide, which is basically that, and you're making 2 DNQ of the aqueous sodium hydroxide, which is that. So the mole of these is equal to, well, they're not equal because you see these 2 mole and this 1 mole. So I should really set up my equations, which is sodium hydroxide and Na2O. As I mentioned in the previous lecture tutorial, it doesn't matter which way around it is because one of it is what you know. You have the masses, that we can work out the MR from the periodic table given the relative atomic masses. So what I can do from the balance equation, I put NaOH on top and there's 2 from the balance equation and there's 1 of Na2O. On the other side is the actual mole that reacted. So I have 62 grams. And then to divide by the molar mass, I kind of need to show my working on this side, how I get the molar mass. So that's 23 times 2 plus 16 times 1. Press it on your calculator, 23 times 2 plus 16 times 1, I get 62. So there is mass in gram divided by the molar mass in gram per mole, because molar mass is the mass for 1 mole per 1 mole, okay, of the substance. At the bottom, I have, actually I've done this wrong. The 62 grams is for the sodium oxide, so that should be at the bottom. Okay, so anyway, so be careful what you put on top. Make sure it relates to, whatever is stated on the top there. That's why it's important to label. If we don't label, it's very easy for us to, not spot our mistake. So on the top there is sodium hydroxide. I have 2 dm cubed, and I want the concentration. Concentration here refers to the molar concentration, so it's mole per dm cubed. So I would say concentration of NaOH in mole per dm cubed times 2 dm cubed will give me the mole of NaOH. Now my job is to make concentration the subject. So there's just 2 over 1 times 62 over 62, and then the whole thing is divided by 2 because the 2 comes down, so it's just times 1 over 2. So I hope you can see without using your calculator. Of course, you can use your calculator. The 2 and the 2 cancel out. The 62 and the 62 cancel out. You just get 1, and you get 1 mole per dm cube. So you can press that to your calculator and you should get the correct, well, the same answer. I don't know whether it's correct or not, but I'm assuming I didn't do any mistakes, so that should be all right for that 2 marks there. The next question is 4-mark kind of question. So the whole question starts from there. In the first part, they say name the raw material used as a source of calcium carbonate. So we can say we use limestone. So limestone contains predominantly calcium carbonate. So they are also used to make very nice marble kind of building like Taj Mahal. Among the many famous buildings, they are made of limestone. Now in part B, we have sulfur dioxide. So carbon dioxide is CO2, sulfur dioxide is SO2, calcium carbonate is CaCO3, and then you produce calcium sulfite. Be very careful about the spelling. This is calcium 2 plus and SO3 2 minus. I just want to remind you that this is in your paper 3, qualitative analysis, where you have differences between the SO3 2 minus and SO4 2 minus. Make sure you can spell this. Make sure when the time comes, you know that SO3 2 minus come from SO2 because there's an underlying chemistry with these, which we'll talk about when the time comes to environmental chemistry. So write an equation. They never tell you to balance it, but if ever you write an equation without balancing, then you are in very big trouble because you shouldn't be doing chemistry to begin with if you don't want to balance equation. So calcium carbonate, Ca2 plus, CO3 2 minus. As you know, there's Ca2 plus and CO3 2 minus. The simplest ratio of which is one of these and one of that. So that plus SO2 will give you CaSO3. And they say carbon dioxide as well. So carbon dioxide is a case study in the simple covalent molecules, one of the many simple covalent molecules that you're expected to know the formula and state the formula just based on the name itself. Well, let's look if it's balanced or not. One calcium. This SO2 take away one oxygen, it becomes SO3. This lose one oxygen, it becomes CO2. So this equation is balanced just like that. So that's B part 1. B part 2 is basically a mole calculation kind of question. We are working with the idea of tons, and 1 ton is equal to 1000 kilogram. 1 kilogram is equal to 1000 gram. And when we do mass over mR, the mass is in gram. So they are trying to give you this relationship here. So there are two ways of doing this. You could convert everything into gram, but then you're going to calculate the mass needed, which will most likely be in tons anyway. So I'll show you the shortcut first, and then I'll tell you something why it should also work if you use it in gram. So I have my calcium carbonate, and I want to react it with sulfur dioxide. So sulfur dioxide and calcium carbonate. So hopefully you can see the mole of calcium carbonate over the mole of SO2 is equal to 1/1 from the balance equation. 1 mole of calcium carbonate reacts with 1 mole of SO2 from the balance equation. That is equal to, now I'm going to put in the actual mole of calcium carbonate that reacted, is to do with the masses. So what I'll do on the side is I will just very quickly calculate the MR of calcium carbonate. So if you look from the periodic table, calcium has a relative atomic mass of 40. 40 times 1 plus 12, which is the atomic mass for carbon, 12 times 1 plus 16 times 3 because you got 3 oxygen. So the MR of calcium carbonate is 100. I do not need to write down the unit because it's assumed that you know MR means the mass for 1 mole, meaning it's gram per mole, gram for 1 mole, the mass for 1 mole. SO2, so 32 relative atomic mass for sulfur, plus 16 times 2 because I got 2 oxygen, so there's 64 there. So I'm dealing with masses here. I'm going to use 960 tons for the sulfur dioxide. So 960 tons, okay, divided by the molar mass, which is 64. And because I use this mass in tons, that means my conversion factor will have the mass of calcium carbonate in tons as well. So T there refer to tons, divided by the molar mass, which is 100. So the tons conversion factor is going to cancel out, okay, because this is mass over MR in tons over gram per mole. This is in tons over gram per mole, the unit is going to cancel out to give you the mole ratio of 1:1, which have no units. So as long as I know that I'm working in tons here, the answer here will be in tons. They don't require you to give the answer in tons, but it's just a bit of sensible mathematics. So I know it is in tons, so I can move this up there, and then there's equal to that, and I can move the 100 up there. So I'm just going to do everything in one step, and hopefully it will make sense to you. I removed the t there just to not want to confuse you with t being a variable. It's just the unit in tons, which I already specify on the left hand side, so I'll never get confused because I stated it, so that I will believe on my own handwriting and I will not get lost. So this 1500 tons of CaCO3, and I know that because I label everything very clearly. If I had chosen to work in gram, then here I will have multiplied by 10 to the 6 gram. Here I will have multiplied by 10 to the 6 gram. Well, essentially I don't multiply by 10 to the 6, I guess. So then it will be in gram. If I chosen to multiply by 10 to the 6, then I'll have times 10 to the 6. I'll have times 10 to the 6 gram of calcium carbonate, which is going to be a huge number in terms of gram. And that's why I chose to work in tons, where both these masses are in tons, and therefore the unit will get cancelled out, and therefore I still get the same answer, except that this is already in tons rather than in gram. Okay, I hope that makes sense to you. Moving on to the next example, so we have ammonia. So this is an equation of nitrogen monoxide. This is steam. This is not water. This is steam because H2O in the gaseous state is what we call steam under states of matter as well as lower secondary science. This is oxygen, and this is nitric acid, H plus and NO3 minus. Nitric acid is a mixture. It's dissolved HNO3 in water. Now I want to get the mass of nitric acid. If I want the mass, most likely I will need to work out the MR of HNO3, because mass over MR, right? So 1 plus 14, well, I can probably show you 1 plus 14 plus 16 times 3, straight from the periodic table, the sum of the relative atomic masses. And then I will have to use this nitrogen 2 oxide as well as HNO3. So I need to compare these and these together. So what I could do is I could compare that HNO3 over the NO. Again, it does not matter which way around it is because it's just mathematics. As long as you could do it correctly, no one can fault you. From the balance equation, based on what I labeled on top is HNO3, so I got 4 on top there. At the bottom, I got NO, so there's 4 from the balance equation. So 4 is quite a big number. I hope you can see that 4 over 4, 4 divided by 4, cancel out to just 1 because 4 divided by 4, 4 divided by 4, they have a common factor. They are both divisible by 1. Or you can think about 4 divided by 4 as just 1. On the right hand side will be my actual mole. On the top is HNO3, so this will be my HNO3. I want the mass of HNO3. So how do I relate mass to mole? I divide it by the MR, so mass over the MR of HNO3, that will give me the mole, the actual mole of nitric acid. Now I have this being a gas, and this is given in volume, so this is volume of gas, because you know how to read the information given. This is a gas, this volume of gas, so I'm talking about room temperature and pressure. Given in the periodic table, you have molar volume of gas being 24 dm cubed for any 1 mole of any gas. 1 mole of any gas has this volume called molar volume. So I have 720 dm cubed divided by 24 dm cubed per mole. dm cubed and dm cubed cancel out, I get mole of the gas. Now I just need to make the mass of the HNO3 the subject. So I can move this up there. So 1 times 720 over 24. And I can move the 63 up there again. So it's just multiplied by 63. If you are not familiar with how fast I have done this question, then I suggest you to do it in step by step. But this one will be in gram because it's gram over gram per mole. Mass in gram divided by molar mass in gram per mole. My final answer has a unit. Without unit, it will have no meaning whatsoever. Last but not least, I have these questions involving tartaric acid and potassium hydroxide. So this is a base, this is an acid, I get a salt, I get water. This is basically a neutralization reaction where you are able to write an ionic equation. H plus plus OH minus give you H2O. This is an ionic equation for all neutralization reactions, and we cover this in the ionic equation topic, where ionic equation without that symbol have no meaning whatsoever. Okay, that's not the focus of this question, however, since we need the mole ratio. So I'm just showing this, I guess for the fun of it. I don't know, if everything is fun, then there will be no learning at all, I guess. But if you find joy in learning, then you enjoy learning chemistry, I guess. So what do I have here? I have potassium hydroxide solution. I have 6 cm cube. Don't forget, this is cm cube of the solution. This is not volume of a gas. And I have solution of tartaric acid. And I want the concentration of the tartaric acid. I also have the concentration of potassium hydroxide up there. So what I'll do is I will have tartaric acid, the mole of tartaric acid over the mole of KOH. From the balance equation, tartaric acid is just 1 mole. Despite the scary looking formula, it's just 1 in front and it's 2 mole there. 1 mole of tartaric acid reacts with 2 mole of KOH from the balance equation. Now onto the actual mole that reacts. Tartaric acid has a concentration. So I'll have concentration of tartaric acid in mole per dm cube. I have 6 cm cube of potassium hydroxide, but I have 20 cm cube of tartaric acid. So read your information very, very carefully. On my label here, on top is tartaric acid, is 1 mole, is the concentration of tartaric acid, multiplied by 20.0 times 10 to the minus 3. So what happened then is, I don't really need to, show the 20.0 over 1000, because it's the same thing. 20.0 cm cube is equal to 20.0 over 1000 dm cube, or I could simply show it in terms of 10 to the minus 3 dm cube. It's the same thing if you have done mathematics. This is exactly the same as that. Just make sure you know that these two forms are the same. I am writing this form is the same as me writing this form. Just choose either one and know that they are the same. As long as I convert this to dm cube, multiply by mole per dm cube, I'll get the mole of tartaric acid on top there. So I have the concentration of the potassium hydroxide, so 0.100 mole per dm cube, and I need 6 cm cube, 6.00 cm cube, so I convert that to dm cube as well. Now all I need to do is make the concentration of the tartaric acid as the subject. So if you make it as a subject, so what happened then is all of that at the bottom there will go up and this will come down. So it's half time 0.100 times 6.00 times 10 to the minus 3, and what will come down will be 20.0 times 10 to the minus 3, and that should evaluate to 0.015. As you can see from the data given, this is 1, 2, and 3 significant figure, 1, 2, and 3 significant figure, 1, 2, and 3 significant figure. So based on the data given, they are all 3 significant figure. Your calculator just show you 1 and 2 significant figure. To be appropriate number of significant figure, we should give it to 3 sig fig, because these are the very kind of thing that they don't really specify in the question, but it's just down to your hang on, let me delete that because that seems to be a bit disturbing. Okay, so that was just the ionic equation for the neutralization just now, so not that important. Anyway, going back to the idea of what is appropriate number of significant figure, it's based on the data given in the question. Experimentally speaking, you cannot get greater accuracy than the data you're given, and you should always refer your final answer to the appropriate number of significant figure based on the data given. So this is 3 sig fig. I'm just writing out as such. I'm pretty sure if you put down 0.015, you wouldn't be penalized because the question did not specify. It's just a matter of understanding the practicality of accuracy, especially if you're doing physics, biology, and also chemistry. Alright, so that's it really. This is the last lecture tutorials where in this lecture tutorial, I'm just going through a couple of work examples on the various concepts that we touched about involving reacting masses, molecule to mass over mR, and we talk about solution where we have molecule to concentration time volume of the solution in dm cubed, and also reacting volume of gases where we have to use the molar volume of gases as well. All right, so yeah, do catch more tutorials in the associated work related to the mole calculation and stoichiometry to see how they are applied across even more examples and across different settings. See you in the next lecture tutorial. Click the button on the bottom right to subscribe to the channel. Share the channel widely with your network of friends, chat group, juniors, seniors, relative, anyone else you think the channel might be useful for. And yeah, follow me at ptet.chemistry. That is ptet.chemistry on IG, Facebook, and Twitter. Thank you for watching and see you in the next lecture tutorial.